Okay, we'll start in a couple of minutes. So I still see people joining, so we'll give a couple of minutes for people to join. Sound check, is that better? All right, so I make it about 5 past, and people seem to be joining slower, so I guess we'll get started. So welcome everybody to IETF 110, and we're online again rather than in Prague, but I guess we're getting used to this. So this is the IRTF open meeting. My name is Colin Perkins. I'm the IRTF chair. So for perhaps the first time this week, a reminder that the IRTF follows the IETF intellectual property disclosure rules, and that by participating in the IRTF meetings and the IETF meetings, you agree to follow the intellectual property disclosure procedures, and that if you make a contribution to the meeting, then you must disclose if there's a patent or a patent application relating to that contribution. And if you need the details, please follow the link on the slide and look at the RFCs listed. In addition, a reminder that we may be taking audio or video or photographic records of the meetings, and certainly this session is being recorded and is going out live on YouTube, as well as being recorded for the proceedings, and will be available on the IETF website afterwards. And in addition, please remember that we encourage people to work respectfully with the other participants, and if you have any questions or concerns about the behavior of participants in the IETF, we have the Ombuds team who will help deal with that, or please talk to me if you have any concerns. And the IETF Code of Conduct and the anti-harassment procedures also apply to the IRTF and the IRTF meetings. So the goals of the IRTF. The IRTF is a parallel organization to the IETF, which focuses on some longer-term research issues relating to the internet as a whole, while the IETF does engineering and standards making. The IRTF is a research organization. It's not a standards development organization. and while the IRTF excuse me, while many of the IRTF research groups co-locate with the IETF meetings to encourage discussion and cross-fertilization between the two communities, the IRTF is not a standards development organization. And while the IRTF can publish informational or experimental RFCs, the primary goal is to promote collaboration and teamwork and to explore some of the research issues relating to the internet protocols, applications, architectures, and technologies. RFC 7418 is an IRTF primer for IETF participants, which may be useful to those of you who are not so familiar with the way the IRTF works. We have a number of ways you can stay informed about the work the IRTF is doing. We have the IRTF Announce mailing list, and you can see that the URL for joining at the bottom of the slide here, which is a low volume list for announcements. We also have the IRTF Discuss list for discussion of internet research related topics. We have the main IRTF.org website, which has information about the organization, links to all the research groups, the prize-winning talks, the workshops we organize. We're also on social media. We're on Twitter. We're on Facebook. We have a LinkedIn page, which unfortunately isn't linked from the slide. And we have we have a presence on the SIGCOM's Slack channel as well. So look out for us on the various social media forums. The IRTF is organized as a set of research groups, and there are 14 research groups currently, and of which 13 of them, all of the research groups, apart from the decentralized infrastructure group, are meeting later this week. So please do look out for those sessions in the agenda. I believe the next one is the measurement and analysis for protocols group, which will be meeting in the slot immediately after this one. And we, as I said, the IRTF also publishes RFCs. The only RFC published in this cycle on the IRTF stream is RFC 8975, which talks about network coding for satellite systems, which came out of the network coding research group. But I expect there'll be a number of RFCs from the Crypto Forum group and from the Information-Centric Network group, which will be published in the relatively near future. There's a number of them getting close to publication. And in addition to the ongoing research groups, we also run, in conjunction with the Internet Society, we run what's known as the Applied Networking Research Prize. And this is going to be the main focus of the session today. The Applied Networking Research Prize is awarded to recognize the best recent results in applied networking research, and it's awarded to recognize interesting new research ideas that are potentially of relevance to the internet standards community, and to recognize upcoming people that are likely to have an impact on internet standards and technologies. In particular, we're trying to bring in people who would not otherwise engage with the IETF and with the IETF community, and try and give exposure to ideas or people that would not otherwise get exposure or would not otherwise be able to participate in the discussion. The details of the prize, we can see that the URL, the irtf.org/ANRP, and you can find links to all the past prize-winning talks there. We award 6 prizes each year, 2 for each meeting typically, and we always get a large number of nominations. I think there were 70, about 70 nominations for the prizes this time. So this is reasonably selective, and we've got some really nice talks coming up and some really people doing some really nice work. The talks for today, the prize-winning talks for today, I'm very pleased to announce from Francis Yan, who will talk about his work on machine learning for video bitrate adaptation, first of all. And that will be followed later in this meeting by a talk from Audrey Randall, who will be talking about DNS caching and privacy and using DNS snooping to detect malware. And as I say, we've got these two really nice talks coming up later, and they're also archived on the website, and you see the URL on the slide. And we'd like to thank the Internet Society and Comcast and NBC Universal for helping organize and for sponsoring this, for sponsoring these prizes. And in addition to the Applied Networking Research Prizes, we also run the Applied Networking Research Workshop. And this is organized in conjunction with ACM SIGCOM, and is an academic workshop that co-locates with the IETF meeting in July each year. And I'm pleased to announce that the ANRW this year will be chaired by the program chairs will be Andra Lutu and Nick Feimster, and it will be happening in conjunction with the IETF 111 in July this year. And the call for papers should appear later this week. The paper submission deadline will be the 21st of April, and this is again a forum for applied networking research, a forum for the internet research community, network operators and the standards community to come together and discuss recent results, emerging ideas in applied networking research. So if you're doing networking research, please do consider submitting your research to this conference. And we're looking for both academic and industry-related research and the broad spectrum of applied networking research. So please do consider submitting. And that's about all I have to say. The remainder of this meeting, we have the two Applied Networking Research Prize-winning talks, starting with Francis Yan, who will be presenting the learning in situ, and then Audrey, who will be presenting on Truffle Hunter. But before we get to that, I just want to pass over to Matt Ford from the Internet Society, who sponsored the Applied Networking Research Prize, to say a few words. Matt, it's over to you.
Thanks very much, Colin. As Colin mentioned, most of today's meeting is taken up with the talks from the Applied Networking Research Prize winners, and I want to say that it's an honor for the Internet Society to be able to support the IRTF in delivering the ANRP. And in its 10th anniversary year, I had to go back through the website and look at the past prize winners and realize that this is in fact 10 years since we started this initiative. And I think the talks, the ANRP prize winning talks, remain a highlight of the IETF week, whether that's in person or virtually as it is now. As Colin mentioned, we've received sponsorship from Comcast and NBC Universal. They are long-standing supporters of the ANRP. If you know of or think of another potential sponsor for this, do please get in touch with me. My email address is pretty easy to find. It's ford@isoc.org. I'd be very keen to add to that list of sponsors for the ANRP if at all possible. So congratulations to Francis and Audrey, and I look forward to listening to your talks today. Thanks.
Okay, thanks, Matt. So with that, we should get started with the talks. The first of the two talks today is by Francis Yan. Francis is a senior researcher at Microsoft Research and Azure for Operators, Office of the CTO. His research seeks to improve network systems by creating learning-based algorithms that can be practically deployed. And he completed his PhD in computer science at Stanford University recently. He's received the NSDI Community Award and the ATC Best Paper Award for his PhD research. And before his PhD, he graduated from Tsinghua University, where he received a BS in computer science and a BA in economics. And he's going to talk to us today about learning in situ, a randomized experiment in video streaming. And the talks are pre-recorded. Francis is on the chat if you have questions during the talk, and otherwise we'll have plenty of time for discussion after the talk. Okay, if we can play the video.
Platform we built to run a randomized experiment on real users and a learning. Hello everyone, I'm Francis from Microsoft Research. My research has focused on practical machine learning algorithms for networked systems. It's my pleasure today to talk about Puffer, a video streaming platform we built to run a randomized experiment on real users and a learning-based adaptive bitrate algorithm that works on the wild internet. This work was completed back at Stanford, advised by my former PhD advisors, Keith Weinstein and Phil Levis. Now let's get started. The problem we're tackling here is adaptive bitrate streaming, or ABR, which is a critical algorithm used to carry a large portion of the video traffic on today's internet. At a high level, ABR aims to improve the user's quality of experience, or QoE. That basically consists of two primary goals: higher video quality and fewer rebuffering events. Although it seems to have been well studied in the past, ABR still remains a challenge because its two primary goals naturally conflict with each other. Let me show you how ABR works. An ABR server divides the video into chunks. Each chunk is usually 2 to 6 seconds. Then each of those chunks is pre-encoded into a couple of compressed versions at different sizes and video qualities. The objective of ABR is to react to the varying network conditions over time and decide which version of each chunk to send, so as to optimize the total QoE of the client. This problem is non-trivial because, let's say, ABR believes it's okay to send 1080p all the time, which gives the highest video quality. But what if the network capacity suddenly drops to a level that's unable to deliver 1080p anymore? From that moment on, the playback buffer in the client's player will be drained slowly, eventually resulting in video freezes. This talk will be in 3 parts. First, I'll describe Puffer, a live streaming platform for video streaming research. Then I'll show a surprising finding from a randomized experiment we performed on Puffer. That is, the confidence intervals on the performance of ABR algorithms are much bigger than we realized. Lastly, I'll introduce Fugu, a machine learning-based ABR algorithm that was learned in situ, meaning in place on the actual deployment environment Puffer. Okay, let's move on to Puffer. To study video streaming and test ABR schemes in real life, ideally on real users, we built our own video streaming platform called Puffer. It's a live TV streaming website open to public in late 2018, allowing users to watch 6 TV channels for free. Our goal was to create a realistic testbed and a learning environment for the community to investigate video streaming algorithms. And we operate Puffer also as a randomized experiment of ABR schemes. So each time you visit our website, puffer.stanford.edu, you'll be randomly assigned to one of the ABR schemes being tested. including those in the prior work and our own algorithm that I'm gonna introduce later. But you won't be aware of this assignment. While you're watching TV on Puffer, our server will record which ABR algorithm is used, along with some other client telemetry on video quality and playback buffer for analysis purposes. To recruit users, we purchased ads on Google and Reddit for keywords like live TV. The other users we attracted came from the press articles covering Puffer. For example, New York Times recommended Puffer to those who need free TV to watch at home during the pandemic. As of today, we've had more than 130,000 real users across the US. Puffer's webpage may look simple, but you can think of it as a small YouTube TV built from scratch. It's actually a lot more challenging to support 130,000 users than building a research prototype. This picture shows Puffer's architecture. We receive TV signals with an antenna at Stanford, decode the signals and encode video into multiple versions, and then serve them using different ABR algorithms to our users. We've also built a monitoring system to monitor the system state and send an alert to my phone if anything goes wrong. We wrote more than 30,000 lines of code for Puffer and have used it to stream 60 years of video to 130,000 real users. Not only our results in the paper are reproducible, all the user data collected on Puffer is being automatically posted to the website every day after anonymization. You could select any data and view the algorithm performance we plotted in figures, but you could also download the data and do the analysis using our scripts by yourself. Additionally, we're opening Puffer to the research community to train and test novel ABR algorithms, and more generally speaking, also congestion control and bandwidth prediction algorithms. And after building Puffer, we then ran a long randomized experiment on video streaming in real life on real users. It's worth noting that the existing ABR algorithms did real experiments as well. But those experiments often run between a few network nodes and lasted for only hours or days. What we have found is measuring ABR performance on the wild internet is much harder than we realized before. You may need 2 years of data per scheme to reliably measure a difference like 20%. I'll demonstrate the surprising finding using the experimental results comparing 5 ABR algorithms. This figure shows the algorithm performance using the data collected on a single day in January 2019. Puffer streamed more than 17 days of video to about 600 users watching TV on that day. Since I'm going to present this type of figure several times, let's take a closer look first. On the y-axis, it shows the video quality measured by a standard metric as SIM. Higher is better. On the x-axis, it displays the rebuffering ratio, but we have reversed the axis, so the better is to the right. Overall, the better QE is up and to the right. For now, let's ignore the individual performance of each scheme and focus on those 95% confidence intervals around each point. You see, even after streaming 17 days of video, the confidence intervals are still huge and overlapping with each other. As a result, most schemes are still indistinguishable from each other. This tells us if you perform an experiment that only streams 17 days of video, you can't really measure any benefits reliably. Any improvements you found could just be statistical noise if you don't collect enough data or consider the confidence intervals. So we left the experiment running for a week and collected 42 days of video. Now the confidence intervals became smaller, but not actually enough. For instance, let's look at the scheme MPCHM. Its mean style ratio is about 0.4%, but the confidence interval ranges from 0.1% to 0.9%, twice as large as the mean value. So we continue the experiment. After a month, about half a year of video were streamed, and now the confidence intervals became much smaller. However, we're still unable to distinguish some schemes. For example, MPCHM and BBA have almost identical performance. But is that a reliable result? After running the experiment for 8 months, we ended up streaming more than 13 years of video to about 55,000 user IPs. And finally, let's zoom in on this figure. We're now able to narrow the confidence intervals down to 20% of the mean value. But remember, this is only possible after streaming at least 2 years of video per scheme. The reason for such large uncertainty is because the internet is way more noisy and heavy-tailed than we thought. Among the 600,000 streams, only 4% of them had any stalls, meaning the other 96% never stopped. Stall events are so rare in practice, which is why you need a huge amount of data to measure them. Additionally, we have results in the paper to show that the distributions of watch time and throughput are also super skewed. In the final part, I'll describe how we leverage machine learning to train an ABR algorithm in situ, meaning in place on Puffer. The first step we took was to understand the system dynamics better. We can plot how the playback buffer changes over time. For instance, it drains 1 second per second while waiting for the next chunk. And once the chunk is received and appended to the buffer, its buffer size increases by the chunk length. You'll see the only uncertainty in ABR is the transmission time of a video chunk. That is simply how long it takes for a client to receive a video chunk since the chunk leaves the sender. The algorithm we proposed is called Fugu. At its core, it uses a neural network to predict the transmission time of each chunk. The transmission time predictor, TTP, takes as input the sizes and transmission times of past chunks, and also the size of the chunk to send. I'd like to emphasize that we don't predict throughput, because a throughput predictor wouldn't consider the size of the chunk to send and would have ignored a well-known fact in networking that the observed throughput actually varies with the file size to send. Another uncommon feature of the input is low-level TCP statistics from the kernel, such as RTT and congestion window size. This is weakly crossing layers, with information flowing from transport layer to application layer. The output of TTP is unusual too. Instead of a point estimate, it outputs a probability distribution over transmission times. And we found it to be useful when maximizing the expected QoE. In sum, TTP has several uncommon features in the design, and our ablation study found each of these features to be necessary to Fugu's performance. TTP's design enables it to be trained in situ, meaning in place on real data from the deployment environment buffer. The training data are sampled and fed into TTP as individual user streams. Each user stream contains a chunk-by-chunk series, including the size and actual transmission time of each chunk, and the required TCP statistics on the server. We use standard supervised learning to train TTP to minimize the difference between its predictions and the actual transmission times of chunks. Note that learning in situ does not require any network simulators or replay any recorded throughput traces. Because if an algorithm is learned in simulation and evaluated in the real world, the gap between simulation and reality may cause generalization issues, which we'd like to avoid. Once the only system uncertainty is approximated by TTP, the remaining question is how to actually select the version for each video chunk. What Fugu does is to look 5 chunks ahead and optimize the total QE in a look-ahead horizon. Roughly speaking, the QE function includes higher video quality, lower quality variation, and less rebuffering time. Given TTP, this optimization problem of maximizing QE can be solved with a well-known technique in Markov decision process called value iteration. We don't need to look into the formula because it's basically dynamic programming, which can be computed in real time. Its behavior is also interpretable because we know exactly what's going on. After the optimal plan is computed, Fugu only takes the first step and then replans for the next 5 chunks. This is also a classical technique in control theory called model predictive control, which proves to mitigate the accumulation of errors. Putting everything together, including the buffer video server, the model-based controller, and TTP. Fugu falls into a class of reinforcement learning or RL algorithms called model-based RL. We first deploy a version of Fugu on Puffer's video server, and Fugu's model-based controller will plan ahead and select the bitrate when it receives necessary information from the video server. The optimal plan of chunk qualities is computed in real time with dynamic programming, during which TTP is queried to predict transmission times repeatedly for the chunks of our interest. After new data is collected and aggregated, we retrain TTP offline using supervised learning and deploy the new version of Fugu on the next day. This paradigm I just described is model-based reinforcement learning, but its core component is really the TTP, which is learned in situ. Once again, let's come back to this figure that shows average video quality on the y-axis and style ratio on the reversed x-axis. The better QE is up and to the right. These results are obtained by analyzing 13 years of video data sent in more than 600,000 video streams from Puffer. Here are 4 state-of-the-art ABR algorithms. BBA is a simple buffer-based ABR algorithm published at SIGCOMM 2014. It selects video bitrate based only on users' playback buffer level. MPCHM and robust MPCHM are 2 variants of an ABR scheme from SIGCOMM 2015. It leverages the classical model predictive model same as in Fugu's model-based controller. However, it tries to predict the future throughput using the harmonic mean of some past throughput measurements. The last ABR in this figure is Pensieve from SIGCOMM 2017, which is also based on reinforcement learning. Different from learning in situ, Pensieve requires training in network simulators. Although their paper reports near optimal performance in simulation, unfortunately, its performance did not generalize from simulation to the real internet. For instance, although its rebuffering ratio is lower than BBA and MPCHM, its average video quality is worse than them. In this figure, Fugu is here. It achieves the highest video quality and lowest star ratio, except robust MPC has a lower star ratio than Fugu, but that comes at a great cost of video quality. This table contains the raw performance numbers of the same experiment, where the first row is Fugu. We can see Fugu's mean star ratio in the first column is only 0.01% higher than the lowest scheme. And Fugu is the best on the other dimensions, including the mean SM we saw in the last slide. In the third column, we see Fugu's quality variation is also the lowest, meaning that the video delivered by Fugu is more smooth than the other schemes. The last column shows an interesting performance metric, time on site, or session durations. Recall that Puffer users are blinded to the assignment of ABR algorithms. Under this randomized setting, users whose sessions were assigned to Fugu chose to remain on the Puffer video player about 1 to 3 minutes longer than on average than those assigned to other schemes. Let's now move on to their cold start performance. That is, how well they perform in new sessions, which they hadn't streamed any video to. We plot the average video quality of the first chunk served in such new sessions on the y-axis, and the startup delay on the reversed x-axis. On a cold start to a new session, prior work argues that since the ABR algorithm knows nothing about the network conditions of the new session, it needs some session clustering algorithm to determine the initial chunk quality based on other similar sessions. Otherwise, ABR algorithms will have to choose the first chunk blindly, which could be too conservative or aggressive. We don't know. By contrast, Fugu provides an alternative option. Recall that one of the input features of Fugu's TTP, is TCP statistics, such as RTT measurements, which are actually available as soon as the underlying HTTP or TLS or TCP connection is established. And knowing this information turns out to allow Fugu to begin safely at a higher first chunk quality than the other schemes, while maintaining roughly the same level of startup delay. To conclude today's presentation, I introduced Puffer, a video streaming platform that we built for the research community to train and test novel algorithms. It has 130,000 real users now and has streamed more than 60 years of video. Using the data, we had a surprising finding that the internet is way more noisy than expected. You may need as much as 2 years of data per scheme to reliably measure a 20% precision. We outperformed existing ABR algorithms consistently in the real world through the design of Fugu. And Fugu's core component is a neural network TTP that predicts the transmission time of each chunk. TTP is trained in situ, meaning on real data from the deployment environment buffer. That's all for today, and I'm happy to take questions. Thank you.
Okay, thank you. Excellent talk there from Francis. Francis, if you want to turn on your video, I see we have a whole bunch of questions and conversation in the chat. I hope not everyone has spent their whole time asking questions in the chat, and there are some left for Francis. So if anyone has any questions for Francis, but please join the queue.
Yeah. Thanks. I think I missed the question. Okay, so regarding the watch time, so time on site is definitely a useful metric for the industry, but the observation we had is that users chose to just watch Fugu longer than the other algorithms. And there's a CDF graph in our paper. And typically for sessions longer than 5 minutes, users tend to stay with Fugu. But other than that, we really don't understand the reasons and what other factors there might be affecting that user behavior. And other question is, can Fugu predict whether having a lower base quality in the manifest of encoded qualities would eliminate more stalls? Okay, yeah, that's a good point. Thanks, David, for the question. We already have a more fine-grained bitrate ladder compared with, I believe, most of the industrial players. We have 10 versions for each video chunk, including 4 resolutions with different CRF encoding parameters, and we spread out, the bit rates. We have a dashboard to monitor whether the 10 bit rates are evenly spread out in terms of their bit rates, the sizes, and their ascent values. So we picked 10 levels, and it's the lowest base quality. I believe our base quality is already low enough for users. Yeah. Okay.
Okay. If anyone wants to jump into the audio to ask questions as well, then we have that.
Let's see, slide 29. Give me a second. Okay. When calculating the median versus the mean, show similar spreads in quality. We didn't calculate the median values, but I would assume they showed similar results. Did I miss any other questions?
It seems everyone's jumping into the chats there. Maria, do I need to press something to?
Yes, let me see how that works.
Yes, I can hear you.
Perfect. So I'm not a specialist on video coders, but you have a couple of other there that you compared with. Are these used in practice, or do you have any knowledge about what the big video platforms are using and how this would compare?
Oh, your question is about bitrate or the other ABR algorithms?
The other ABR algorithms.
The other ABR algorithms. So the BBA, so I would say all the other 4 ABR algorithms are research algorithms. And in terms of industry adoption, I think probably BBA, a variant of BBA, is used by Netflix because it was proposed by one of my friends, actually my colleagues at Netflix. So it's a heuristic-based algorithm, simple algorithm based on only the buffer size. And for MPC and robust MPC, they were proposed in SIGCOMM 2015, and Pensieve was proposed in SIGCOMM 2017. They are both research algorithms, so that's why we compared with them, but I'm not sure if any real video service providers are using them.
Yeah, I mean, I read some papers where they try to kind of understand how these algorithms work, and it's usually kind of a black box thing. But the one thing I kind of got from is that these algorithms also kind of change very frequently. So it's probably interesting to find out more there, but also hard as a researcher. Thank you.
Yeah, no problem. And actually, I would say they're not as black box as we thought. So for instance, BBA is pretty simple. So below a threshold of the playback buffer size, maybe 3 seconds, we ask the video server to send the lowest quality. And above maybe 12 seconds, we send the highest quality. And between 3 seconds and 12 seconds, they use a linear, linear interpolation between different bit rates. So that's pretty interpretable. Thanks, Ali, for thanks. And Ali in the chat, Netflix never confirmed or denied using BBA or anything else. I think when we gave a talk, so BBA was proposed by T.Y. Huang when she studied at Stanford with advice by Nick, and then I believe.
Yes, but that was a decade ago, so it's I'm sure Netflix has advanced since then.
Yeah, and when we gave a talk, the Puffer talk at Netflix, yes, they didn't reveal any confidential information, so I'm not saying anything not allowed. But you are right. So maybe they have deployed or are using a variant of BBA, or maybe not. Well, I don't really know, actually. Has there been similar work on video conferencing systems? Zoom, Jitsi, Meet, Echo. Yes. So ABR's corresponding work in video conferencing is bandwidth estimation, or broadly speaking, also congestion control for real-time video. And it also adapts to different, varying network conditions by changing the sending bitrate of the video encoder. And actually, I'm working with Ali, so we're hosting, Microsoft is organizing a grand challenge on bandwidth estimation for real-time communications. We're hosting it as a grand challenge at MMSIS this year. And Ali has been kindly helping us putting things together, sort things out. Yeah, thanks for sending the link.
So Jonathan had a question, I think.
Hiya, can you hear me?
Yes.
Did you have a chance to look at the P99 or the P99.9 performance? So the performance of the very tail of Fugu.
Yeah, that's a good question. Let me see. I don't think we reported any percentile or tail performance in the paper, but we did look at them. And especially in those figures, we have included the confidence intervals. So we're confident that that interval has the mean value. The P99, P95, honestly, I don't have the answer, but I believe we checked before. Yeah, I agree that tail performance is critical.
Thanks.
Thanks for the question.
So can you maybe say something about some of the difficulties or challenges in running a sort of research experiment as a grad student at this sort of scale? This seems to be one of the larger experiments in this space.
Yeah. So in my experience, having real users is like having real impact on the world, and that's super exciting to me. But the availability, I would say, that's the biggest challenge. Usually when we write some code, it can work 99% of the time, but if real users are watching it all the time, then the system should never go down like too frequently. And as soon as Puffer stops working, I would receive user complaints in emails. So I'm essentially on call 24/7. I have so that's why we built a monitoring system. So anytime there's a bug making the service crash, I would receive an alert. So ahead of our user emails. Thanks our users for letting us know, of course. So I will always try to, maybe I'm in the middle of night, I will still get up and fix the bug immediately. So that's the biggest challenge, availability. And especially for me, almost the only engineer working on developing the platform, it's really hard to maintain it. Yeah. And I'd like to add one more thing. Yeah, so we are testing research schemes. So research code is, I don't want to say this, but research code tends to be messy. So even though our code is of relatively high quality, but when we run other algorithms, use their research code on the production system, and it also crashes many times. So that's a pain.
Yeah, it's a challenge. It's a challenge. My other question, to what extent is, I mean, obviously the specific results you've got are relating to video, but to what extent do you think the types of issues you're running into with needing to do very large scale, very long running measurement studies apply to other types of network measurement research? Do you think you'd find the same issues of confidence intervals and so on if you repeated other types of network measurement experiments?
Yes, I would expect the findings to generalize to other network measurements because so we did see heavy-tailed user behavior, but we believe most of the part of the reasons why we observed the noisy sliver of the internet was because of the network, network per se, the inherent issues and heavy-tailed nature of the network. And my past research has studied congestion control, and we observed also very different findings from those reported in previous research papers. Because when you measure congestion control on a larger real-world test bed and over many times, we tend to see different results and noisy results.
Okay, thank you. All right, does anyone else have any questions for Francis?
Jonathan wonders if it's a question of code optimization. So are you talking about the research code or anything else? Yeah, okay. I'm not sure how to solve this issue, like running research code on a production system. I think typically people will just reproduce or fix potential issues, potential bugs in the research code. But in our case, we want to faithfully compare with other algorithms. and report and evaluate their performance. So I think it's challenging to consider both aspects. Compare server compute time for the algorithms. Yeah, that's a good question. For our algorithm and another deep reinforcement learning based algorithm, yes, we have to take into account the compute time and the compute resources required. But fortunately, none of the algorithms consumes too much compute resource, and it takes just typically several milliseconds to compute the decisions, APR decisions online. So that's not a bottleneck. So we did look at the compute time, but we didn't report it in the paper because it was not a bottleneck, just to be clear.
Sure.
What information was included in the state updates to the MPC controller? I think you're asking about Fugu's model-based controller, right? So the information includes the past 8 chunks, their transmission times and the sizes, and also the size of the chunk to send, and also low-level TCP statistics. So those are the input features as the states, and they're also the updates provided to the controller. Sorry. So those are the inputs to TTP, to the transmission time predictor. And for the model-based controller, the input is the current playback buffer level and all the necessary chunk sizes, because it needs to run this dynamic programming, also known as value iteration algorithm online. So that's all it needs.
All right, so last question from Roland.
Yeah, last question. So does it leave a slow start often? So first of all, the Pensive paper in SIGCOMM 2017, if I remember correctly, they disabled the free, like the timeout, the TCP timeout, such that it never, or it hardly leaves the slow start. It hardly leaves the congestion avoidance phase. So it doesn't return to the slow start phase, because when you send a video chunk every 2 to 4 seconds, we don't want congestion control to ramp up every time starting from the slow start phase. So we can definitely disable it. But in our case, I believe we also disabled it. So it shouldn't go to or stay in slow start very often.
All right, so thank you, Francis. Really nice talk, some really good discussion there. I would normally say that Francis will be around for the rest of the week, and you should grab him in the break if you have any questions. Clearly, this is a little bit difficult, but hopefully Francis will be able to join the Gather Town in some of the breaks, or drop him an email or on the chat if you want to talk further about this work. So thank you again, Francis. Excellent talk.
Thanks for having me.
Thank you. All right, so at this point we will move on to the second of the prize-winning talks today, which is by Audrey Randall. Audrey is a third-year PhD student studying internet measurement and security at the University of California, San Diego. Her research interests center around measuring and understanding harmful behavior on the internet, from underground crime to stalkerware to DNS hijacking. She received her bachelor's degree in computer science from the University of Colorado Boulder in 2018. And her talk today is on cache snooping rare domains at large public DNS resolvers to detect malware. So if we can play the video.
Hey everyone, my name is Audrey Randall. I am a PhD student at the University of California, San Diego, and I'd like to talk to you today about our paper Truffle Hunter, cache snooping rare domains at large public DNS resolvers. When you think about abusive behavior on the internet today, you might first think about the more common types, such as spam emails or botnets or malware. All of that stuff is everywhere. And the thing about it is it's easy to find in the wild simply because it is so common. But there's another type of abuse which is much harder to find because of its rarity, and that includes things like typo squatting, hack for hire services, stalkerware services, where we really don't know how many people are affected by it because it's hard to find in the wild for whatever reason. So that's the type of abuse that we are really interested in studying. And we've made the observation that all of these types of rare harmful behavior have something in common, which is that they all need to make DNS requests to the servers they require to function. If you could observe enough DNS requests, you could presumably study these types of harm in more detail. You could figure out how prevalent they are, where they occur, how frequently they occur. But to do that, you're going to need to observe a lot of DNS requests because you're looking for the needle in the haystack. You're looking for a very small amount of signal in a large amount of noise. Fortunately, we're kind of entering this new era in DNS right now, and that's because these public DNS resolvers are starting to gain more popularity. It used to be that it was only power users and people who were really tech savvy who would be using public resolvers, but we're starting to see them get hard-coded by default. For example, Google Home routers all use Google's Quad 8 service by default, and Firefox routes all their DNS queries to Cloudflare. We even see that New York City's entire public Wi-Fi network now uses Quad 9. So, of course, we are not Google, we are not Quad 9, we are not Cloudflare, but can we, as third-party observers, still use these services to observe the kind of rare behavior we want to study? Well, of course, the answer is yes. There is a well-known technique that's been around since at least 2004 called DNS cache snooping. But in the past, it's been presented as an attack, and it's considered a privacy threat, and for good reason. Most of the time, what researchers were doing when they did cache snooping was they would scan the whole internet, and they would try and see which devices would answer a DNS request. The problem was, most of those devices were misconfigured home routers, so they've only got a few users behind them, and if you find some domain on them that might be invasive of privacy, it's not too difficult to figure out which actual user put it there. Public DNS resolvers, on the other hand, allow you to preserve privacy. Because so many people use them, it's almost impossible to de-anonymize them. It's almost impossible to figure out, just based on the fact that a domain is in cache, who put it there. So that's great. We can use cache snooping as a measurement technique instead of a privacy threat on public resolvers. But public resolvers are also more challenging because they've got complicated caching strategies, and that's why they're of interest to the IETF, because this does lead to some protocol noncompliance. So for the remainder of this talk, I'm first going to go over some brief background on cache snooping for anyone who hasn't seen the details in a while. And then I'm going to talk about how to do it on public resolvers. To do that, you need to understand their caching strategies. So we as researchers had to reverse engineer the caching strategies of 4 large public resolvers. Next, I'm going to talk about our tool, which is called Truffle Hunter, and how we used it to measure certain case studies and learn a little bit more about these types of rare abuse that we're interested in measuring. So I'll get started on background of cache snooping. So if somebody were to make a request for example.com to their local DNS resolver, that resolver would have to look at its cache and say, all right, is example.com present? If so, they can return the response quickly to the user. If not, they have to go to the authoritative name server. What you can do if you are a snooper is make a request for example.com, but set a flag that tells the resolver it is not allowed to check the authoritative name server. That way, if you get a valid response back with a valid IP and a valid TTL, or time to live value, then you know that the domain was cached. I should note that all of the resolvers we've been using this on do respect the recursion desired flag, with one slight exception, which I'll get into later. But the thing about cache snooping as a measurement technique is that it only provides a lower bound on the number of users that are accessing a domain. So if multiple users have hit the same cache for the same domain before that TTL expires and the record is removed from cache, you won't be able to observe them. You can observe a maximum of 1 user per cache per TTL. But that's okay for our purposes because we're looking for the types of phenomena where nobody knows how frequent they are, how frequently they occur in the wild, and it's valuable even just to get that lower bound because seeing any of them is actually really bad news. But cache snooping on a single resolver is actually reasonably straightforward. In order to do it on a public resolver, things get significantly more complicated. So let me talk next about how public resolvers work in broad terms and then how they work in more specific terms. When a user wants to send a request to a public resolver, that query is first routed using IP anycast to the first available or the closest point of presence, or POP. Once there, it can be routed to one of any number of front-end caches. There are a lot of these. And if it misses in those front-end caches, it will be sent to one of usually several back-end resolvers. So that's good for us in some ways because each of those caches represents another possibility of observing a user in the wild. But of course, these complicated caching techniques make our job a little bit harder because we need to be able to count how many caches our queries have hit, and we need to be able to differentiate between them so that we don't double count full caches. This challenge is exacerbated by the fact that each of these public resolvers implements their caching differently, and we have found that that inconsistency could cause potential problems. While some of the resolvers we've looked at always do seem to serve records with correct TTLs, we have found some that can either serve records with incorrect TTLs or will serve records after the TTL should have expired. So in a few slides, I'll go into more details on that. I've mentioned that in order to do our measurement study, we need to count how many caches have been filled with a domain, and that means we need to be able to identify which caches our queries have hit. So we had to understand the caching strategy of each of these 4 public resolvers. To do that, we only have access to the TTL and the timestamp of the DNS queries that we were sending, which made reverse engineering these things kind of challenging. So I'll go over now how we did that. We ran an experiment where, from a single central location, we would repeatedly query a resolver and try and fill its caches. Then we looked at the query responses that came back, and we looked at their TTLs and their timestamps to try and figure out how the caches worked. At this point, I have to introduce the concept of a TTL line, which is just our model of how a TTL decreases in a cache. A TTL in a cache ought to decrease by about 1 second per second. So if you plot a bunch of measurements that have all hit the same cache, you ought to see, if you plot their timestamp against their TTLs, that decreases by 1 second per second. And that's this green line in the figure here. That's our model of what the TTL should be doing in the cache. When we do that against real resolvers, in this case OpenDNS and Quad9, we get something like this. It looks like about what you would expect. Now, note that this plot is zoomed in on the first 50 seconds just to show detail, so the TTL lines aren't shown going all the way to 0, but of course we expect them to do that eventually. The first thing that you might notice is this row of measurements across the top, which came back with the maximum TTL value for the domain we used. They're circled in red. We assume that each of these measurements filled a new cache because they came back with the maximum TTL value. And we were able to confirm this because we controlled the authoritative name server for the domain that we were querying. So we confirmed that every time our authoritative name server got a new request, we got a measurement back at our measurement source with a maximum TTL value. You'll also notice that all of the measurements that are not one of the top row of circled dots lie on one of the TTL lines. So they look like they came from one of the caches that we observed to be filled. So that's great. That means that OpenDNS and Quad9's caching architecture is reasonably straightforward. Requests can hit any of several independent front-end caches, and if they miss, they're sent to a group of independent back-end caches. And we can just count the TTL lines that we see and assume that that's the number of filled caches. When we ran this experiment on Cloudflare, we got a very different looking graph. So we do get a first measurement, which came back with the maximum TTL, but all of the measurements after that look like they came from the same cache, which we would have thought would be unusual in a resolver of Cloudflare's size. You can also see that for a while, the measurements look like they're exactly on the TTL line, but then they start to drift over time, and we notice that they would always drift upward. So what we think is happening is that Cloudflare has a shared front-end cache, shared and distributed. As soon as a measurement arrives in one cache, it is shared with all of the others. So that's a little bit disappointing for our purposes, because at the whole pop, we can only see one cache get filled. So we can only measure one user per pop on Cloudflare. There is a question with Cloudflare's strategy of whether or not it is completely compliant with the DNS RFC for TTLs. The maximum drift that we saw of away from the true TTL value was about 80 seconds. So we were using a domain at the time with a TTL of about 3 hours, and we saw that there were still measurements in cache whose TTLs hadn't yet expired for about 80 seconds after they should have expired. Now, it's important to note that the drift scales with the maximum TTL. So probably, even if you have a 60-second TTL, you're only going to have a drift of a few seconds, and that's probably not going to be an issue for you, even if you have such a short TTL. And if you have a long TTL, you're probably tolerant of more drift. So we concluded that the actual problems here are likely to be very small. And then finally, we looked at Google DNS, which is the resolver where the caches fill themselves. This actually isn't just our observation. There's been prior work that has observed this as well. Champ et al. Found that they could make requests and get an accurate TTL back on the original requests, but then they would keep making requests and they would find subsequent TTLs to be wrong because it looked like those TTLs were coming from caches that had never been filled. And then Reprimardo et al. Noticed the same effect and called these mystery caches ghost caches, which we thought was a great name for them. So why on earth are these caches getting filled without being queried? I'll show you what we mean here. If you look at all of these blue lines, you will notice that there is no measurement at the start of these blue TTL lines, these mystery caches. According to our theory, every filled cache should correspond to two things. A measurement that we made with a maximum TTL at its start, and B, a request to our authoritative name server. And we didn't see either of those here. What we eventually noticed is that every light blue cache does appear to get filled at the same time as one of our measurements was made. You can see that the dotted lines that descend from the start of each cache line each pass through a measurement. So what we think is happening is this. Google is using what we call a dynamic caching strategy. When a request comes into Google and it misses in a front-end cache, that's this light blue cache here, then it's going to get forwarded to a backend cache. And let's assume that that backend cache is already full and it has a TTL less than the maximum value. The first time that TTL less than the maximum value, let's say 550 seconds, is going to get sent back to the user. But at the same time, the front-end cache is going to store the record, and it's going to store the maximum TTL, which in this case, let's say it's 600 seconds. So you can think of it like this. Every request that comes into Google DNS has a chance to spawn a new cache that is visible to cache snooping. So that's great news for us as researchers running a measurement study, because we will see a much greater percentage of unique queries on Google than we will anywhere else. But you do have the question of whether this strategy is going to lead to inaccurate TTLs. Now, we did observe that if we queried a domain that we had placed in cache and we queried it all the way until its TTL expired, these ghost caches, or these front-end caches that we filled ourselves, they did expire even if the TTL had not reached 0 yet when the original backend cache expired. So that's good. But we noticed that a user could make a request just before the TTL of the backend cache expires and get a cache that had just been filled, and that could lead to extending the TTL to twice as long as it should be. So the maximum drift is just twice as long as whatever the maximum TTL is. Whether or not this is actually a problem is not up for us to decide. We couldn't think of a use case where it would be super problematic, but we do have a question of why would this be a useful strategy? Why store the maximum TTL in the front-end caches rather than just copying the TTL from the back-end caches? Now, it's great that Google did this from our point of view because it really enabled our measurement study, but we couldn't come up with a reason why it would be more efficient or more performant to do that. So if anyone is here from Google or if anybody wants to weigh in, I would love to get somebody's thoughts on that when I'm done with this talk. So to summarize, OpenDNS and Quad9 appear to have a pretty straightforward caching strategy. And we don't think that that caching strategy ever manipulates the TTLs of the responses at all. Cloudflare has this shared and distributed front-end cache, and we do notice that the TTLs are affected slightly by it, but we don't think that's likely to be too much of an issue because the drift is so small compared to the length of the maximum TTL. And Google has what we call a dynamic caching strategy, and that can result in a TTL received by the client being about twice as long as it should be, because you could receive a maximum TTL right before the backend cache's TTL was set to expire. So you should have been receiving a very small TTL, and you receive one that's closer to the maximum. Now that we've talked about how to use cache snooping on public resolvers by counting the caches that your queries hit, let's talk about our tool, which we have nicknamed Truffle Hunter. It's our distributed measurement tool, which we've deployed on Kata's Archipelago project. That means it's on 46 different measurement nodes scattered across the United States. All that it does is send continuous DNS queries across the US for the domains that we're interested in. When it gets the responses back, it interprets them according to our models to try and figure out how many caches were filled, and we go from there to estimating counts of users in some cases. We have 3 months of data, or did at the time we wrote this paper, from March to May in 2020. Truffle Hunter is, of course, not perfect, and the first big question that we had when we deployed it was how accurate it was at estimating the number of caches that were filled, because we know that our models of cache architecture might not be 100% accurate. So we ran an experiment where from 900 different ripe atlas probes, we placed a domain we controlled into the caches of public resolvers. The idea was just to put it there as if people across the US had done it naturally. Then we used Truffle Hunter to try and observe it in those public resolver caches. Because it's a domain we control, we could conclude that the number of requests that came into our authoritative name server should be the true number of filled caches, except in the case of Google, which of course does its own thing. We found that we performed best on OpenDNS and Cloudflare, except in the case of one particular Cloudflare POP where we think there was some routing going on that we didn't account for during our experiment. On GPDNS, it turned out to be difficult to accurately remove all of the front-end caches that had been filled by our own probes, so we conservatively removed more than we had actually created in order to ensure we never overcounted. That's consistent with our goal of always providing an underestimate rather than an overestimate of the number of caches that have been filled and therefore the number of people that are filling them. And then Quad9 was very interesting. It had the same architecture as OpenDNS, so you would expect it to be just as easy to snoop. But as it turns out, Quad9 runs 2 types of software at each of their backends, and one of them refuses to respond to non-recursive queries. That's Unbound. So if it turned out to be that Unbound was the software that had cached our domain, that record essentially became invisible to us. So it does mean we can't observe about half of the filled caches at any Quad9 POP. The takeaways here are, first, we were able to tune our algorithm so that we almost always underestimate, which is good because our goal is to provide these lower bounded estimates of prevalence. And second, even on the resolvers where we have high error, we do see at least half of the filled caches. The next limitation that Truffle Hunter has is inherent to cache snooping as a measurement technique, and that is that you can only observe one user per cache. So we looked at how many caches were visible on each of these resolvers at any one time. we found that Google had a great many of them that were visible to us because of their dynamic caching strategy, about 100 times more than either OpenDNS or Quad9. Cloudflare, of course, only has one visible cache per pop, so its graph is omitted here. OpenDNS and Quad9, you might notice that some of the larger pops like NYC and IAD have a lot more visible caches than the smaller ones. So that's Truffle Hunter in a nutshell. Now, the interesting bit is what we actually use Truffle Hunter to study, and that's our case studies, which I'll talk about next. We ran 4 of these. I'm only going to talk about 3 of them here. And these were stalkerware, contract cheating, and very old typo squatting domains. We didn't expect to see very much of any of this stuff for various reasons. And previously, all of these things were kind of difficult to measure. Maybe typo squatting not so much, but certainly contract cheating and stalkerware have been very difficult to observe in the wild. And nobody really had any data about how prevalent they were. First of all, let's talk about stalkerware. If you haven't heard the term before, it's kind of this emerging spyware threat. It's this software that can be installed on a target's device, either a phone, usually a phone, or a desktop computer, and it tracks them. It can record location. It often has keyloggers to record texts, social media, browsing history, things like that. And oftentimes it can record ambient sound and video of the device as well. And it can hide its presence on the device. So even if you are downloading it on an Android phone, which ought to tell you how many apps and what types are installed on it, it can hide its icon so that you can't tell it's there. So we downloaded and profiled 24 of these apps to try and get their network signatures so that we could figure out what DNS requests they were making. 6 of these apps were what previous work calls dual use. Those are apps that have a legitimate purpose, which is separate from their ability to stalk somebody, but they can be repurposed to act as stalkerware. The line between dual use and overt apps is a little bit blurry, but dual use apps tend to be marketed for parental control or employee surveillance or things like finding a lost phone or backing up your data, rather than for spying on a spouse or a girlfriend. Overt apps, on the other hand, are marketed as undetectable and marketed specifically for, or at least often marketed specifically for, spying on a spouse or a girlfriend or a husband or what have you. So they tend to be the more dangerous ones. The prevalence of overt stalkerware is hard to estimate by any other means because it's very difficult to observe it in the wild. Prior work in this space has mostly been conducted in clinical settings. So researchers will conduct individual one-on-one interviews with targets, and unfortunately that gives them a low sample size. During these interviews, they found few to zero of these overt apps in the wild, but a simple Google query will turn up dozens of them, and there are ads all over the place. So it really does beg the question of how much of this overt stalkerware is out there. Additionally, by the time a target has come in to talk to a professional, they have often already reset their devices. So it's difficult for a clinic to tell which apps were on there before the reset. And finally, clinics often lack technical expertise. So if they aren't working with someone who does have expertise in this space, it can be very difficult for them to tell if a device has stalkerware installed. Up until this point, we've only been talking about counting filled caches, not counting the number of devices that have made the requests. And we haven't made any attempt to differentiate between a single device that is making multiple requests and multiple devices that are each making a single request. Stalkerware is a really good app to use, a really good use case to use for figuring this out, because it's supposed to be often installed without the user's knowledge. So it has to make its DNS requests automatically without any user interaction. And that means it often makes them at regular, predictable intervals. So if you want to know how many devices have stalkerware installed, all you have to do is measure that request rate and then divide the number of filled caches you see by the request rate of the app. That's the technique that we use to come up with this figure here. This graph shows the maximum targets that we ever observed with stalkerware installed at any one time across the United States. We found that nearly 6,000 people are being targeted by overt stalkerware in the US today, and recall that that's a strict lower bound. The number may very well be higher, but we suspect it's not lower. The two most interesting apps that we found were called Mobile Tracker Free and Spy to Mobile. Those are the two most frequent that you can see at the top of this chart. Mobile Tracker Free, we suspect, is so popular because out of all the overt apps we studied, it was the only one that wasn't subscription-based. It was free to install, free to use. And Spy to Mobile, while not being free, was the only one of the overt apps that was available on the Google Play Store because it has a habit of changing its developer name and its name and re-uploading itself multiple times to evade Google's rules. We also looked at the dashboards for stalkerware. And when I say a dashboard, I mean the website that an attacker will go to when they want to view the data that have been collected by the app. We again see that Mobile Tracker Free is the one that was visited most frequently, but Spy to Mobile has fallen down in the rankings a little bit. So clearly it is the case that the popularity of the app does not necessarily correspond to how many times somebody is checking the dashboard. We theorize that might be because of differing app capabilities. Mobile Tracker Free has a lot more features than Spy to Mobile. Spy to Mobile is mostly good at tracking location. And the next case study that we looked at was contract cheating, which is the new form of plagiarism that the kids are using these days. So in case you haven't heard of this, these are services that you can buy as a student to complete your homework or your projects or even entire classes for you. I've even seen a few that are offering to get entire online degrees. It's pretty hard to detect when a student is using this because they're not actually plagiarizing. They're not copying work that exists already. They're hiring someone to create original content for them. Of course, your mileage may vary. Some of these services are better than others, but there are a few that are good enough to get A's in most cases, even including college and sometimes graduate classes. So it's of course hard to observe in the wild because students aren't going to just admit that they have done cheating, even on anonymous surveys, which is how a lot of this work has been done in the past. So we had Trouble Hunter look for it, and we observed that yes, you see a lot of requests per day to these contract cheating websites. Now, of course, a request made for the website doesn't necessarily mean that a student bought anything, but it's still an interesting number to observe. We saw that some of these services, which we measured over the last couple weeks of May, were decreasing over time, which we thought was interesting and might indicate that schools are letting out for summer break, so demand for cheating is going down. And then finally, because we had some of these domains, we looked for typo squatting. These domains are pretty old. We don't expect that they are being used to phish anybody anymore because received wisdom in prior work says that phishing domains and typo squatting domains usually roll over very quickly. They get blacklisted and then the miscreants move on to other domains. So you wouldn't expect that any of these would still be receiving DNS requests, but we saw that yes, they are still getting a few requests per day, which is interesting. So the takeaway from our point of view is that cache snooping on public resolvers shouldn't actually be gotten rid of yet. We argue that there are minimal privacy concerns when you're cache snooping on public resolvers because there are too many users to figure out which user put a domain into cache. And if you allow cache snooping on these resolvers, then you can measure types of harm that are otherwise very difficult to study. In particular, for stalkerware, it's very difficult to figure out how much of this stuff exists in the wild, and each instance of stalkerware represents a significant amount of harm being done. Furthermore, contract cheating is difficult to study because students are just not honest about whether or not they've bought cheating software. And then there's other phenomena which we didn't get a chance to measure very well, which we would like to look into more in the future, such as these new hack for hire services and phishing, which by all accounts is quite common, but we would like to see how much of it is happening in various places around the world. To conclude, we found that public DNS resolvers enable us to use cache snooping as a privacy-preserving measurement technique rather than an attack. We think this is a valuable measurement technique that should not be disabled on specifically public DNS resolvers. We also found that to use cache snooping on public resolvers, you have to understand their cache architecture, which is quite complex. So we reverse engineered 4 of these resolver strategies, And we did find that Cloudflare and Google caused some minor TTL non-compliance. Whether that's an actual issue or not is not up for us to decide, but we suspect it's not that much of a problem. And then finally, we used our tool to find non-trivial lower bounds of the prevalence of internet phenomena that were previously very difficult to study. So Truffle Hunter is open source. If you want to try it out for yourself from a single location, you can go to this GitHub link at the bottom of the slide. And I'd like to thank you for your attention and take questions at this time.
Okay, thank you very much, Audrey. Excellent talk. I see there's a bunch of discussion in the chat there. If anyone wishes to ask questions in the audio, then please go ahead. Please join the queue. I don't know if Audrey has, yes, there you are.
Sorry, figuring out. Oh dear.
I can see you and I can hear you.
I'm getting quite a bit of echo. Let me just plug in the headphones real fast.
Sure.
All right, Colin, can you say something?
Yeah, is it working better now?
Yes, I believe so. Okay, so there were a few questions in the chat that I haven't had a chance to get to yet.
Okay, and there are people in the audio queue as well.
All right, so to Andrew's question about resolvers offering malicious content filtering, we were using the services that provide content filtering, but the thing about stalkerware is that it usually isn't filtered because most threat feeds didn't consider it a threat until very recently. It's kind of an emerging threat, so people haven't been focusing on it too much until just the last couple of years. And the problem with trying to block stalkerware is that, first of all, you have the dual use issue. So you could be blocking a legitimate app that is being used for a legal purpose. And second, if you block it, then you have the risk of making a stalker think that the person being stalked is trying to leave the toxic relationship or trying to take action against the stalker. And research suggests that that is the point at which surveillance can turn violent. So it's not necessarily a good thing to block this stuff, so most threat feeds don't. Let's see. Jim asked where we got the domain names for contract cheating services. They're very easy to find if you Google them. So what we're measuring is hits on the main landing page for each of these services when you just get there from a Google search. Let's see, and then the list of typo-squatted names came from, I think, a couple of older papers, which is why we wouldn't have expected to see any of them and why it was interesting that some of them were still getting, you know, up to 100 hits per day.
I think Jonathan has a question in the audio.
Hi. The number of dual use technologies seems very low compared to the amount of stalkerware. Is that what you actually measured, that dual use is less common than stalkerware?
The particular dual use apps that we measured did seem to be less common than the most common types of overt stalkerware, but there could be a number of reasons for that. So first of all, we didn't measure as many dual use apps by choice because people know more about the dual use ones, about their usage and their prevalence already, and what we really wanted to know was the overt ones. So we may not have found the most popular ones. We do find, based on previous literature in this space, that most surveillance is actually not done by the overt apps. It's done by, you know, misconfigured sharing settings or whatnot. So that was the really interesting thing we wanted to find out, was why the overt stuff was there.
Interesting, thank you.
Okay, Jim?
Great work, Audrey. I think this is an excellent presentation. Could you say a little bit more about the RD bit setting stuff? Has that had any influence on your work or on the behavior of the caches that you're measuring?
I'm sorry, you cut out for just a second at the end.
Sorry, you mentioned earlier in the presentation about the RD bit setting on the queries. Could you say a little bit more about how that's influenced your work or the behavior of these resolver caches?
Yes, so the kind of cache snooping that we're doing wouldn't be possible without poisoning the caches ourselves, without using the recursion desired bit, because if the recursion desired bit is off, of course, you make the query, and if it isn't in cache, then it won't get put into cache. Google was the exception to this, because we found that if we had hit a back-end resolver that had the query cache, and then we hit a front-end resolver that did not have the query cached, a front-end cache that did not have the query cached, then the record would be copied from the back-end resolver to the front-end resolver. So our own probes would fill the caches there, and we did find that it was a challenge to remove the poisoning that we had done. And then, as someone just pointed out in the chat, yes, so unbound will return a refused response when you try and make a query with the recursion desired flag, which was why we could only measure half of the caches at quad 9, because if they had a resolver with unbound software that received the original query, then it became invisible to Truffle Hunter. Does that answer your question?
Okay.
Yes, it does. Sorry, I didn't realize I still had the mic.
So I see some discussion about whether it's desirable to enable the ability to respond to RD equals zero queries in the chat.
Yeah, so I think the issue is that the issue with whether or not to enable recursion desired is you want to enable recursion desired if you want to enable these types of measurement studies on resolvers where there are few to no de-anonymization risks for users, and those are the large resolvers. If you are running DNS resolving software and you know that it's going to get put on small home routers, which can be used as, misconfigured open resolvers, then I would say no, you want to have defenses against cache snooping, and sure, that could include not allowing queries with recursion desired unset. So the question is how large the resolver is.
This may be something where it's worth chatting with some of the folks in the DNS operations group.
Yes, absolutely. I would love to do that.
So there's a question
Yes,
about results from around the world.
Yes, Jonathan is saying it would be, sorry, I'm getting some echo again. Did I do something? Okay, yeah, Jonathan was saying it would be great to see results from around the world. Yes, so the measurement platform that we're using, which is how we get results from around the United States, doesn't have quite as many nodes around the world, but yes, it would be great to expand to that.
What would it need to do that? Do you need to change platforms? Or?
No, it would actually probably be reasonably straightforward. We were keeping our experiment to the United States in the first place so that we wouldn't add too much load on their system. And then it just ended up that that was the data that we had to publish our results. We are at the moment working on expanding a similar tool to Truffle Hunter, but instead of measuring domain usage, we're trying to measure DNS hijacking, and we do want to expand that to worldwide using similar techniques. Vladimir is saying that default settings aren't targeted for huge instances like those studied. I don't know if you want to elaborate a little bit more on that. Are we talking about enabling recursion desired or not in large public resolvers? Yes. Yes, I think having the ability to enable it or disable it based on what kind of what kind of resolver you're running, the size of the resolver you're running is probably the best solution.
Okay, I can't tell, Jim, are you still in the queue to talk?
Sorry.
Okay. So I had a question. I mean, we're seeing, you know, obviously people making increasing use of you know, different types of DNS transport, you know, over TLS or over HTTPS, and we're seeing new techniques like oblivious DNS that are getting proposed. Do any of these make a difference to the type of work you're doing?
DNSSEC and DNS over HTTPS or DNS over TLS do not affect our work because the queries still get cached the same way. You mentioned oblivious. I haven't actually heard of that before.
Yeah, this is a new thing which I have to say I don't know a whole lot about. It seems to be using encryption and proxy resolvers to anonymize the people making the queries.
Okay. I suspect that as long as those queries are still arriving at public resolvers, then it won't interfere with our technique. But if it provides an extra layer of anonymization for the people making the queries, then awesome.
Yeah. And presumably the DNS over HTTPS would maybe allow some of these some of the stockware apps to make the DNS queries in a more controlled way, so maybe avoid the public resolvers.
Yes, it might. The thing about stalkerware apps is that they tend to be incredibly unsophisticated. They don't try and obfuscate their code at all. Half of them crash as soon as they get installed on the phone, at least on an older device. And they seem to have a lot of bugs and problems in general. So I would be surprised to see them adopting any sophisticated techniques like that in the near future. But there are some that are certainly ahead of the game, like FlexiSpy, that would be more of a problem than the others.
Okay.
Jonathan is pointing out that this might mess with our geolocation. Yes, but I think as we realize, Anycast is not a great way to do geolocation in any case. So, you know, our geolocation is a little bit suspect. We can say that users possibly in a very broad region are experiencing more stalkerware or whatnot than users across the country, but Anycast is not a great way to figure out where users actually are, to the best of my knowledge, in any case. There's some more questions about Oblivious, which I feel like I might not be able to answer.
Yeah, I'm sure some of the people developing Oblivious are probably here, so we can hook you up with them to talk
Yeah,
about
I would love to learn more about that.
Okay, I think it would also be good if any of the operators of these services are around, and if we could try and put you in touch with them as well, that would be helpful.
Yeah, that would be great.
All right, are there any last questions for Audrey before we finish up? No, I guess that's everyone. Well, thank you again to Audrey and to Francis. The two really nice talks, some really good discussion, and I know it's a fairly unpleasant hour in the day for both of them. So thank you for getting up so early to participate in this. As I said at the end of Francis's talk, I'm sure both Audrey and Francis will be around for the rest of the week and will be available if you want to chat with them. So please do get in touch with them if you have any questions or want to talk about any of this work further. And that's all we have for this session today. Look out for the Applied Networking Research Workshop call for papers coming up, and look out for the rest of the IRTF sessions later this week. And the recordings of these talks and the links to the papers are on the IRTF webpage if you want to look into them in more detail. All right, thanks everybody.